Welcome to StableSort. In this episode, we're going to discuss a neat computational problem, a type of a brain teaser that you may have to solve in a coding interview. Suppose you are a leader of a foreign country and you'd like to influence the US presidential elections. All you have to do is grab a credit card, open an account in Facebook, and start posting propaganda ads in swing districts. To keep track of how well your ad campaign is doing, you get a list of these districts, each of which could have a value of either Democratic or Republican. Independents, without ranked choice voting, are essentially throwing away their votes anyway, so thus don't count. So this could be an array of Boolean values: true, false, 0, 1, Democrat, Republican. Given this array of districts, you need to write two methods: isDem, to determine if the district at position I is Democratic or Republican, and toggle, to toggle all of the districts in the range from I to J. But here's the kicker. Both methods should run in less than order n time complexity. Pause the video here if you'd like to solve the problem on your own. The function isDem that checks if a given district is Democratic or Republican is easy to implement either through an array or a hash table. But having to toggle items in a range in less than linear time complexity is what throws a monkey wrench into this approach. No matter what data structure you use, be it a hash table, a tree, an array, or whatever, if you have to iterate through each item in order to toggle it, then it's going to be a linear time operation. Our only other option is to store and manipulate the start and end values of the toggled ranges. So instead of storing the state of each individual district, we store the boundaries of the toggled ranges. Let's take a look at a simple example. We'll start off with all districts being Democratic and then toggle the range 3 to 5 inclusive. The table on the top displays the state of each district for us to keep track of. This is just a visual aid to check if our function returns results that match with this table. The array below, let's call it T, is what we'll use to keep track of the toggle operations. It's a Boolean array, and for convenience, we'll assume 0 to signify Democrat and 1 to signify Republican. So, if the range 3 to 5 is now toggled from 0 to 1, then we mark the start of the range at index 3 and the end of the range at index 6. Note that the middle elements are left untouched and that the end range is marked not at 5, but at next index, 5 plus 1. You'll see why this is important in a second. The trick to solving this problem is that the way we're going to mark the boundaries isn't just setting them to 1, but rather performing an XOR operation, which toggles the value. So if it's 0, we flip it to 1, and if it's 1, we flip it to 0. Then computing a cumulative XOR from index 1 to I gives an answer to whether district I is Democratic or Republican. In this example, note how the cumulative XOR function returns 1 starting at index 3 and then switches back to 0 at index 6, matching with the table of districts. This is why we toggle the end range at the index n plus 1. Let's continue this example and call toggle 5 to 6. We flip the bits at indices 5 and 7, both of which happen to be 0. Had they been 1, then we would have flipped them to 0. Now let's check if we can retrieve the state of each district by running a cumulative XOR from 1 to each index. As you can see, using XOR operator to keep track of a whole range of districts works quite well. Another way of thinking about how cumulative XOR operates is that it sums up the total number of 1s from the beginning of the array to index I. If the number is even, then district I is Democratic. If the number is odd, then it's Republican. Flipping the bits at just the range boundaries is quick. But now the problem becomes the isDem function. Running an XOR operation from index 1 to I becomes a linear time computation. However, there is a data structure called Fenwick Tree, also known as binary index tree, that performs this computation in order log n complexity. If you're not familiar with Fenwick trees, I would recommend watching our previous episode that discusses this data structure in fine detail, including a source code walkthrough. There's a link in the description. The gist of it is that given a list of numbers, once you construct a Fenwick tree, you could do range operations as well as updates in order log n running time. Typically, it's used with add operator to find the sum of numbers in some range I to j. But it also works with XOR operator. Applying it to our problem, the Fenwick tree would store bit values, either 1 or 0. Then, when toggling some range I to j, we XOR the item at index I and index j plus 1. As mentioned earlier, this update operation would take order log n for a Fenwick tree. To read the value of a particular district I, we do a cumulative XOR from index 1 to I, which is also an order log n operation. Thus, both of the methods run in less than linear time complexity. Problem solved! The actual implementation is trivially simple, assuming you have a Fenwick tree, the source code of which you can download from the link in the description. I hope you enjoyed this episode of Stable Sort. If you did, please petition Congress for a constitutional amendment to implement ranked choice voting, or at least click that thumbs up button. If you have any questions or comments, please leave them in the comment section below. And thank you for watching.